Hello everyone, my name is Luca Franco and today I'm going to present a set of measurement of the Higgs couplings to bosons with the Atlas experiment on behalf of the collaboration. Let's start from the standard model Lagrange. So while the first two terms describe the interactions of the gauge bosons with themselves and with the fermions field, the last three ones describe the Higgs potential and its interaction with the other standard model fields. This term here is the one truly relevant for these presentations because it describes the interaction of the Higgs with the other bosons. Among the many Higgs decays, let's focus now on the three bosonic channels. So we have the Higgs decay to Z bosons, the Higgs decay to photons, and the Higgs decay to W bosons. So you can notice that the diphoton decay cannot be described like with a point-like vertex like the other two because the photons is massless. So in order to happen, this interaction must involve a particle loop. So thanks to these three channels, we were able to observe the Higgs back in 2012. But still, nowadays, these are very useful because they allow to study the Higgs properties in various regions of the phase space. At the LHC, the Higgs boson can be produced mainly through these five mechanisms, and I have put here the leading order Feynman diagrams for them. So studying the production rates is important because it can give us access to the coupling to the other particles. So for example, the gluon fusion and the associated production with top quarks can give us information about the top Yukawa coupling, while the vector boson fusion and the associated vector boson production can give us access to the vector boson couplings. I want now to introduce the concept of the simplified template cross-sections because many measurements that I'm going to present were performed within the context of this theoretical framework. In this framework, the regions of the phase space are defined by cuts on some sensitive variables like the Higgs transverse momentum, the number of jets in the final state of the event, etc. And they are also divided per production mode. The first set of measurements that I'm going to present were performed in the gamma-gamma channel. Here we measure the total production cross-section, the cross-section of the five main production modes, and also 27 STXS. This analysis makes massive use of machine learning techniques like boosted decision trees to separate the signals and also to reject the background. The fit is performed by modeling the Higgs peak and the falling background with analytic functions in the spectrum of the invariant mass of the two photons. If you look at the top right plot, you can see that for the GGF and VBF measurements, the systematic component of the uncertainty starts to become similar to the statistical one. This instead is a summary of all the 27 STXS that we have measured. So this analysis was really optimized to minimize the correlation among all these STXS bins. However, we still have some 30% level of correlation between some VH bins. But this is the first channel that is able to perform differential measurements in TTH. And we managed to set an upper limit on the TH production, which corresponds to the most precise measurement so far. The second set of measurement was performed in the WW channel, where each W bosons decay into a lepton and a neutrino. This channel, we measured the GGF and VBF production cross-section and also 11 STXS. The categories on this analysis were defined according to kinematic selection to target the VBF topology and also to categorize according to the number of jets. The background was taken into account using dedicated data control regions and Monte Carlo simulations. In the fit, the observables are the transverse mass of the dilepton system, MT, which is defined by this formula here, for the GGF categories. And for the VBF category, a neural network was used in order to separate the two production modes, and this output was used as an observable. Here we measured 11 STXS bins, 6 GGF-like, and 5 VBF-like. As you can see in some of these measurements, the systematics are dominant. And just to mention some of them, the dominant ones are the contribution from the jet energy scale resolution from the experimental side, or from the theory side, I can mention the Parton shower modeling. In general, the contribution to the overall uncertainty was very large from the normalizations of the background. In the Higgs to ZZ channel, where each Z decays into two leptons, we measure the total production cross-section, the cross-section of 4 production modes, and also 12 STXS regions. This analysis used the data on the sides of the Higgs peak to constrain the ZZ non-resonant background. Many neural networks were used to both separate the different signals and also to reject the background. And then the output of this neural network was used as observable in the field. Here we also, as I said, we measured 12 STXS. In addition, since most of the sensitivity of the VBF production mode was coming from the region where the mass of the invariant mass of the dijet system was high, we also performed a separate measurement there, and this is the result. So the measurements in 3 decay channels, X to gamma gamma, X to BB, and X to ZZ, were combined together to get this extremely detailed picture of the Higgs boson production kinematics. As you can see from the plot, the relative uncertainty are mostly statistically dominated, where in some cases they reach up to 100% value. These STXS measurements are used as input for the various interpretations that I'm going to explain in a moment. So the kappa framework makes a reinterpretation of the measurements that I've shown before in terms of the coupling strength of the various Higgs vertex. So in this picture, you see kappa Z is the strength of the Higgs coupling to the Z boson, and so on for the other particles. Obviously, since the gluon and the photons are massless, the kappa lambda and kappa G refer to these effective couplings where the particle loop involved in the interaction is not resolved. The standard model prediction for this scheme corresponds to the situation where all the kappa equals to 1, and the contribution from the rate to invisible decays and to undetected decays are set to 0. Another approach to perform interpretation of the STXS measurement is through the effective field theory framework. The standard model EFT adds new terms to the standard model Lagrangians, which correspond to beyond standard model operators. And here I have put some examples of this operator and leading order Feynman diagrams for them. The coefficient associated to these operators can be parameterized in terms of the STXS, and then this can be constrained. In this plot, you have an overview of the study of the impact of each operator in every STXS regions. Constraining these EFT parameters means putting limits on many beyond standard model theories at the same time. Unfortunately, we cannot constrain all the CI, so we had to perform a principal component analysis to find the set, the combinations of CI to which we were sensitive, and also to identify the flat directions. Then we managed to simultaneously constrain 10 combinations of these coefficients. And we did this in 2 configurations, with and without the inclusion of quadratic terms in the parameterization. Another important results in the context of DFT is the combination of the measurement of the GGF and VBF production mode in the X to gamma to WW channel, with the measurement of the differential cross-section of the di-boson standard model production. In this case, also the WW background must be parameterized in terms of the EFT parameters. Then we follow the same procedure that I explained before, and we simultaneously constrain 8 combinations of these parameters. So I want to stress that this is a very first important step towards a future global EFT fit, which can potentially include also measurement from other areas different than the Higgs sector. This year in Atlas, we also published the search for the di-Higgs, the double Higgs production in the gamma-gamma BB final state. Using this process, we can constrain the kappa lambda, which is the self-coupling modifier. We managed to set an upper limit of 4 standard model prediction on the HH production, and also we set a limit on kappa lambda at 95% confidence level. The most rare decays, some of the most rare decays of the Higgs bosons are the decays into Z boson and a photon, and the decay into 2 photons, one of which is a virtual photons. Atlas published the first evidence of the decay of the Higgs bosons into photons and a pair of leptons of the same flavor in the gamma star gamma channel, while instead we don't have yet evidence for the other Z gamma channel, but we managed to set an upper limit on this process corresponding to 2.2 sigma level. Finally, we also studied the CP properties of the Higgs, first using the TTH and TH productions in the Higgs to gamma-gamma decays to test the CP structure of the top Yukawa coupling, and we could exclude the pure CP component, and we constrained also the mixing angle. Then we also studied the CP structure of the effective couplings to gluons in the X2WW channel. And in the same channel, we studied the polarization of the HVB vertex. So this already brings me to the conclusions. Today, I've presented many interesting measurements produced using run2 data by Atlas, and all of them were in perfect agreement with the standard model prediction. This is not the end of the story, though, because we expect more results with full run2 data. We look forward to combining them with similar ones from the CMS experiments. The improvements of the precision on the precision of this measurement can come both from new analysis methods, but also from the larger data sets that we expect from the next LHC runs. Thank you very much.